Okay, YouTube, in this final video, we're going to look at a different form of division that we refer to as synthetic division. And it's just an alternative to long division. It is just that when we use synthetic division, it's important to note here, it only works if the divisor is of the form x minus k, okay? And one thing to point out really here is this. Synthetic division, I'm going to type this since I type much better than I write by hand. We say synthetic division. I also type much better when I don't speak as I write it. So we say, okay, so basically what you're seeing here is the truth. We say that synthetic division can only be used if we're dividing by a linear factor, which essentially means this. It has to be a divisor that is first degree divisor. Okay. So when we talk about synthetic division, though, the way we carry it out is we still have some dividend polynomial that we're dividing by some divisor polynomial. It looks like we're taking a fourth degree divided by a first degree polynomial here. And because we're dividing by a first degree polynomial, what we can do is we can use this synthetic form of division. So the way synthetic division works is simply this. We make our division array, except for we tend to make it upside down of what we're normally seeing. And we still put our dividend on the inside and our divisor on the outside. But there are some things of note that we need to point out here. First one is, I noticed that we're missing an x cubed term. So when we fill in our dividend in here, we're going to have to put in 0 x's cubed. And the second thing is that we don't have to put in all of the x's. Really all we need are their coefficients. So I noticed that my coefficients are here 1x to the fourth, 0x to the third, 10 of these x's squared, negative 2 of these x's to the first, and 4 of these constants. So the way this will be set up inside the array is 1x to the fourth, no x's cubed, negative 10 of these x's squared, negative 2 of these x's to the first, and 4 of our constants. Now, as far as what we put on the outside, we're used to putting the divisor on the outside like this. But the interesting thing is what we're putting out here is an actual x value. So the thing I want to point out here is this. If you're dividing by this, x plus 3, then imagining we set this equal to 0, what would be the x value associated with this? And a lot of people say, well, it's just, it's just the opposite of what you see in here, which would be negative 3 when you solve this. So we could put a negative 3 out here, and you could think of it as, well, the opposite of this k value that you're seeing here in this binomial, this first degree binomial. But one thing I want to point out is, if I were dividing by 2x plus 3, and this is hypothetical, well, then really what I would put for an x value on the outside is negative 3 halves. And the reason why I'm getting that is because when I set this equal to 0 and solve it, the x value we're actually using here is negative 3 halves. So because we're dividing by x plus 3, you can think of it as an opposite. We say I'm going to put a negative 3 out here. But this thing right here is our divisor x value that is associated with this potential factor. So now I'm going to go ahead and go through this division here, and we're going to ask the question, well, do we get something that was a factor or is not a factor? In other words, did we get a remainder of 0 or not? So as far as how we do synthetic division, the first step is always this. You carry down your first term's coefficient down to the bottom of this array. This always happens. So once we've carried that down, what we're going to do is we're going to multiply diagonally, and then we are going to add vertically. So just to show you what I mean, we'll start by taking this negative 3 times this 1 right here. And what we get negative 3 times 1 is negative 3. And what that does is it gets carried up into the array right here, and then we will just add vertically straight down. So we get 0 plus a negative 3 is negative 3. So now multiplying diagonally again, we're going to say negative 3 this time times a negative 3, which gives us a positive 9. And I'll put that up here in my array, and then we'll add down vertically again. A negative 10 to positive 9 gives us a negative 1. So now we're going to multiply again diagonally, and I get negative 3 times a negative 1 is a positive 3. And then we'd say, okay, well, negative 2 plus a positive 3 is a 1. Last but not least, negative 3 times a positive 1, multiply diagonally. We're going to put that up over here, negative 3. And then we're going to add vertically, which gives us this value of 1. So here's what I want to do. This that you see right here, we're going to label it thusly. We're going to say that this is the quotient. So we had placed the dividend up here, dividend. Our divisor was this thing out here, divisor. And what I want to do is I actually want to fix this. This is our quotient right here. And I'll put a box around this last name because that thing right there is our remainder. So the way this works is with this division, what we get here is this. The last term is always the remainder. And then going backwards, we're just going to put our variables back in. We're going to say that this is some polynomial quotient in standard form. So what that means is we had a remainder of 1, and that 1 is over the thing we were dividing by, which was not x minus 3, it was, remember, x plus 3. So we have our remainder here, x plus 3, all of this. And then we'd say, well, this 1 right here really is our constant term, 1, positive 1. And then working backwards, I see this negative 1. This really is our x to the first term. This will be our x to the second term. And you just go back and you put in your variables again. So we would say negative 1 x to the first. So I have negative x to the first. And I say negative 3x squared. So I have negative 3x squared. And I have 1x to the third. So I have a positive x to the third. So what we get here really is this quotient where instead of having to do long division, we could just multiply, add, multiply, add, multiply, add, multiply, add, and then get all the way through this. Another thing that becomes perfectly clear, though, is essentially this, that this last term right here was not 0. What we really mean is that we didn't get a remainder of 0. What this also means is that x plus 3 must not have been a factor of this original polynomial. So we're going to make a few comments on this synthetic division thing, and we share these in the forms of the remainder and factor theorems, and then the uses of that remainder that we see here. So in terms of the remainder theorem, this is really profound, but it says if a polynomial f of x is divided by this factor x minus k. Remember, if your factor is x minus k, then the x value we would have put on the outside is that k. We would have put a k out here. It says if it's divided by x minus k, then the remainder is actually r, and r is equal to f of k. So what makes this profound is essentially that it's saying this. The remainder value is equal to the value of f of x at the x value k. In other words, if we were to actually plug that k value into the function, that remainder that you see right there is actually the y value that you would get when you plug this into the function. So keeping in mind that we had just plugged in a negative 3 essentially, this is our k right here. If we were to plug negative 3 into the function, we say f of negative 3, we actually get the remainder value as a y value. And I'll tell you what, that beats the snot out of having to put negative 3 into each of these x's and then go back and simplify it and evaluate it. So one thing that I've done here is in this video, I've graphed that polynomial. We see this here, this green polynomial. I'm trying to get this off. There we go. And we say, okay, well, what are its zeros? Do we have any recognizable zeros? Well, one thing I know is this. We tried to see if negative 3 was a 0, and it was really close. But negative 3 is actually not the 0 here. So if I said, what's the y value of our graph at negative 3? What we were able to determine just a moment ago is that our y value should be 1 if this remainder theorem holds true. So what I'll do is I'll click on this and I'll scroll left until you see here, when we get to an x value of negative 3, check this out. You're exactly at a function value of positive 1. So again, the remainder theorem essentially says when you do synthetic division, this remainder right here is not just the remainder, it's actually the y value you get when you plug this x value into the function. So now let's confront the factor theorem, which, by the way, is the same as the remainder theorem, but stated a little bit differently. They're two sides of the same coin, but it says if this polynomial f of x here has a factor x minus k. In other words, if x minus k is really truly a factor, then we divide this, you're going to get a remainder of nothing. Furthermore, if x minus k is a factor, when we set that equal to 0 and solve it, then it means x equals k has to be a 0. And if x equals k is a 0, that means that when we plug k into this function, you're going to get a y value of 0. So you're an x-intercept if you get plugged into a function and you get a y value of 0. And another name for an x-intercept is a 0. So the thing I want to point out here is this. This can only be a factor if when you divide it, it leaves a remainder of 0. And at the same time, if that is a factor, then x equals k must give us a y value of 0 when we plug it in. So I'm telling you that the beautiful thing about the remainder is it tells you two things. One, it tells you if you got a remainder or not. And if you didn't get a remainder, what that means is this must have been a 0. And if that's a 0, then this would have been a factor. What we witness here is this. Because we did get a remainder, then our graph was not on the x-axis at this x value right here. And therefore, x plus 3 certainly is not a factor because it didn't go in evenly. And furthest most, we could say that our graph's function value or the function's value at this x value here is at 1, which is not at 0, which is not on the x-axis. So when we say, well, what do we use the remainder for really? The big things are these. We say the remainder r gives us the value of the function at x equals k. In other words, it tells us what height is your graph at f of x, or sorry, f of k. Also this, we say, well, if the remainder is nothing, what this would also mean is, that would mean that the k value here is equal to 0. It gives us a function value of 0 when we plug it in. So that would be an x-intercept right there. And also x minus k would be a factor if you don't get a remainder, which is logically something we can follow. And last but not least, if you don't get a remainder, then that k value must be an x-intercept of your graph. It must be a 0.